Hi, my name is Kresten. I'm CTO in Humio. We built a log aggregation tool, which is something you would use if you have a large complex system in production and want to monitor it, debug it, and problem solve things happening in production. Often these complex systems are difficult to really test because they have so many dependencies and so many external tools. So as it happens, here is where we run and operate and develop Humio. And the product that we built, you can see it on the wall there, is a tool for doing log aggregation, for building graphs, and also for debugging. Today I'd like to just introduce you to some of the architecture of the system design, and the trade-offs that we make. So, as I said, Humio is a system that targets people who run a complex 24/7 system. So I've invited one of my customers, Jan Møller. He's CTO in Chainalysis, which is a startup in the Bitcoin space. And maybe you can tell just a little bit about your system.
Yeah, so basically we are running more than 100 servers, and with a really complex system, very many different kinds of systems, and we're using Humio and we're very happy with it. But how does it actually work? Because I'm really curious about that.
Yeah, okay, that's fine. So basically, when you look at it from kind of the bird's eye view, right? A log aggregator is a system where we gather data, right? So you have all your servers running here, and the data comes in. And so Humio is a system that is sort of a database. So whatever we gather logs from, it could be syslog, application logs, web server logs, etc. And on these various systems, we have forwarding agents, or various software that ends up shipping the software, the logs, to Humio. So it all ends up in this database, right?
So, but we use syslog, right? But
yes.
What other mechanisms are there for ingesting?
So, yeah, I think you send all your stuff through syslog, but so we have an HTTP API that is a custom HTTP API. We have that's something that's being used by some applications, some web applications, for instance, that send data directly to Humio. We also have a layer that emulates the Elastic Bulk API, because there's lots of log shippers that actually send data in this protocol, this particular protocol. So there's a range of different. We have some systems integration if you use some of these container orchestration frameworks, like DCOS, that will capture the logs from your system in various ways. So there's a number. This is actually part of the complexity of installing Humio, is to actually get the data in.
Right.
And that's maybe another story for another day. How to get around all that, right? I'm kind of a back-end guy, right? I'm really focused on the stuff that happens when the data enters this point, right? So the reason why I'm drawing this drawing is I'd like to kind of highlight some of the trade-offs that we make, right? So unlike a traditional database, happens is, after some time the data falls out automatically. So either if this bucket runs full, or if some time has passed, we can automatically delete it. Because it's part of an operation system. It's part of your operations. You don't want it to all of a sudden fill the disk, right? You don't want this kind of system to...
So I can basically specify a monitoring window where I'm interested in looking what happened over that time?
Exactly. So the other thing is, of course, like your ops guys or developers, they are, in this context, the users of Humio, right? They have some people sitting here looking at it. So again, unlike most database-based systems, these are not as numerous as typical systems. Often, so if you build an online SaaS service, or if you build a bookstore, online bookstore, whatever, you have hopefully millions or hundreds of millions of users. In this case, there's typically only a few. There's the developers and the operations that look at it. So that's actually an important part of the trade-off, part of the trade-offs in the system. So, And actually, I'd like to draw this little graph here saying, so what's the cost of ingest? Say ingest cost versus the query cost. So if you look at traditional database system, the ingest cost is relatively high because you build indexes and do a lot of work up front so that it's really fast to execute queries. But that's part of the trade-off that you need when you have many users. If you only have a few users, then it's actually okay for a little higher query cost. Every time a user comes by, he typically has the entire machine for himself. So the interesting thing is if you can permit a higher query cost, then you can actually have a very low ingest cost. So that's part of what I want to talk about. That in Humio, it's easy to ingest, say, on a single machine, so a terabyte a day of data because the processing is relatively simple. The downside is queries are somewhat slower, but since there's only very few current or concurrent users, we can still get a good experience out of it.
So what kind of footprint will this system have? So let's say I ingest a terabyte a day. So how much storage would I then need? Because if you have a typical database, then there will be indexes and so forth.
So typically, the storage over here is 10 to 20% of the ingest. You could say this is for a single day, so we compress it 5 to 10x. You could say, and then if you want to keep it for 10 days, then maybe it's a terabyte. One to 2 terabytes.
What I would have been expecting, right? Because normally the data kind of is blown up when you store it in the database, right?
That's right. So this lets you really run, again, say overall the ingest cost is very low because you don't need that much storage, and also as we'll see, we don't need that much CPU to actually take in a high volume of data. So of course the flip side of this is since we don't build indexes, it becomes somewhat more expensive to query it, because essentially what these users do, or this database can do, is table scans. So the kinds of queries that you would do are the things that you could do with a table scan in a database, essentially running over the entire data set. And that could, of course, take some time. So that's something I'd also like to tell you about, how we make that run really fast. Right? We'll get back to that.
Okay, great.
But there's one. So if you look at what a table scan here is, you run some function over the entire data set. You take, say, a state machine and feed it every piece of data. So the data arrives here in these are log lines that happen to come in little packets. Another way to look at this running a table scan would be to run it through just directly into the state machine. So alternatively to running through there, you could just set up a state machine that just fed all the log lines as they arrive. And that it essentially can perform the same computation. If you set up a time window, I only want to look at the last 5 minutes. And that means that you can, if you set up queries like this, there's basically two different ways of running queries in Humio. One is where we just feed the events into a state machine, and one is where we take essentially the same state machine and run it over the data set.
So when I run Humio, I have those dashboards, and they're super valuable. So when am I doing this scan, and when am I looking at this state machine?
Typically, when you show a graph where you see it moving, that'll be actually computed. The entire graph is computed in a state machine like this. That's what we call a live query. Other people call them streaming queries or various other things, standing queries, etc. We call this a live query, but it's the same query language. It's the same. We have the same mechanism for expressing things that run over this or this.
Okay, so it's not something that I have to actively do. So
you click a check mark and say, yeah, I want to run this live, and then it just runs it this way instead. So it takes some time before it has its window full, right?
Sure, yeah. Okay, get it.
So then of course, these live state machines can also be used to feed alerts into to users, right? So this can trigger alerts, etc. So I think this is fine for this. I'd like to move on a little bit and talk a little more on how this ingest process works. So let's see. If we just go back. We'll look a little more concretely on the system architecture. Essentially, we have a front-end node, an API node, we call it, and a back-end node, which is a data node, and all the various ingest mechanisms, they hit the API node, and as data comes in the ingest flow, it gets fed into a queue. It's then picked up by the data backend, right? So this is right now we're using Kafka for this.
Okay. So when I installed Humio, I got this Docker container. So what does that contain? Is that the entire thing, or?
Yes, actually. So the single node install is just one Docker container right now that contains everything. We also provide a container without the Humio, without the Kafka part. If you want to run Kafka.
Okay. So if I have my own cluster, I can run that on the side.
Yes. Yes. So what happens when a piece of data enters here? Essentially, a single log line from some file somewhere. First, it gets validated. Maybe there's user authentication. There's or an application token. If you have a special kind of application token only for ingest, so you can have an ingest token. So we need to do various validation at this point, and then push it into Kafka. And essentially, if you use the HTTP API, then you get a successful response back when it's actually stored in the Kafka queue.
Okay, so as long as my Kafka survives, then my
as long as your Kafka survives. So you could scale this up or down, have a big fat Kafka, then at least it's stored to this point, right? Then the next step on the backend side, it gets picked up, and we have, you could say, sort of a namespace of what we call data space and data source, where the data space is an assigned chosen namespace, and data source is really just the unique combination of tags that you attach on ingest. So the log line will get fed all the way into, this is part of the data component, the data node here. It gets fed into kind of a buffer of log lines, and when it's full, it gets compressed and flushed to a segment file. So it gets appended to the end of a segment file. So segment, we have basically, so this is one of the things that actually surprises many people. We have our own database. One of the most often questions that we get is, so which database are you using to store the data?
Right. So but is that, that segment file, this compressed file, is that a file on the file system, like a classic?
It's just a plain, actually these data spaces are on the SaaS solution that we provide. It's just a plain directory, right? So every user's data is stored in its own directory, and these are really just files in that directory. So, and once you've done, you filled up one of these segments, then it never changes again. Okay. So basically, for a given data source, we have a current, and then we have all the other ones that are finished, right? All the historic ones, and these are completely immutable.
So, but eventually they might get thrown out, right? So I can specify how long retention time I want to have on those?
Yes, so the retention you specify is, of course, each of these have some timestamps associated with them. So you can specify that when they get to a certain age, they get deleted, or if you have too many, then you delete the oldest ones of them.
And maybe can I offload them or to some other place, just doing normal, I don't know, rsync or whatever I want to do?
Yes,
or?
they're just plain files. They get appended to, so it's actually very simple to just offload them. Or you can copy them somewhere else and later import them back into, say, another data space, for instance. So if you have, that's just one of the operations things that we also need. At this point, we have 10 different on-premise installations, various places. Some of them we run ourselves, and sometimes you need to move data around, right? It's nice to be able to do that. For test systems or for moving test data around. Yeah. So there's the core of the data idea is just we have these immutable data segments that we can checksum them, and they're very, very easy. They're on the order of, right now the default is like 1 gigabyte for each of these segments, right?
Okay. So basically, if I have like 5 or maybe even 10 gigabytes of ingest data, they turn into one of those chunks here,
yes.
Depending on how well it can get compressed.
Yes, we typically see the longer the log line, the less compression. So in the demo system that you can use online on humio.com, we take in the live feed of all public GitHub data. And that's some very long, complex JSON structures, and that compresses only 5x or something like that. Whereas if you have nice, kind of classical Unix syslog entries, that compresses 10x typically. So that's the range of compressions, right? So as you can see, there's almost no index actually. And that's when we get to the querying part. There is a tiny index because all these segments files, as I said, they have a timestamp. There's a time. The start, the first, and the minimum and maximum of any kind of timestamp in these log files. So when did it start and when did it end? Each of these, and that's actually information that we keep in memory.
Ah, okay.
So it's also persistent on disk, so we can read it up at start. But essentially, the system knows which segments exist and when was the first and last event in that file.
So basically, what happens if I have a crash? If somebody turns off the server all of a sudden. So of course I would then not have that in memory anymore, right? And
right.
My files would still be there, but
yes. So I mean, the most interesting part of a crash is what happens to this buffer, right? Because this is an in-memory buffer of one of these blocks of data to go into a segment.
That has partially created segment.
It's work in progress for one of these blocks. So this one is half full, so the data in there wasn't flushed to disk. As it happens, well, what we do is actually we go back to the queue here, because in Kafka, every message has an offset. So say the last log line in the previous block, the one that actually was persisted here, say it had offset number 100 in the log. That means we can recreate this work in progress by going back to offset 100 and replay the queue.
So basically, if if my Kafka stream can handle at least one of those blocks, then I would be good.
Yes. So.
And also, and then as you mentioned, on the HTTP API, I get an OK back when it is in the Kafka queue.
Exactly.
Right.
Right, and then actually the log shippers that we suggest you use, if you have files, classical log files, such as like FileBeat is one of those. It monitors a file on disk, and whenever somebody writes out log entries to that file, it pushes them to some remote system, right? And actually, FileBeat will, if it gets back an error, in the case where it couldn't push it to Kafka, for instance, then it'll kind of throttle back and resend them at a later point in time. So that's actually very nice. You have them buffered locally on the source system. They're buffered here, where we essentially use Kafka as a commit log. And every time we flush up one of these blocks, which is about just 1 megabyte of data, we in that block also write how far back you have to go in Kafka to replay from this point forward. So actually we put some effort into also making it resilient, and so you wouldn't lose data on the way in.
Right. And if I then wanted to make it even more resilient, then I can run Kafka outside and have it in, multi-tier.
You can run Kafka outside. There's a couple of different things. Yes. So we have customers running their own Kafka. We have there's also a live backup feature, which is essentially you can set up a separate file storage, like an FTP server or something, and then every time we commit one of these blocks to disk, we'll send a copy of that block to the live backup. That's a file again. This gets encrypted, so you can store it somewhere unsafe, like in a public cloud. And when the system starts up, it'll actually read any blocks that are missing from the system from the live backup.
Okay, so this is kind of an optional thing I can do.
This is an optional thing you can do, and actually you can also turn off this queue if you just want a little more performance. You can just turn off the queue altogether.
Okay.
Actually, that's a config option, whether you even want to run with that. Then it just becomes a synchronous call all the way into appended to that data area. So again, it gets really, if you push in typically 1 terabyte of data through this API, it typically becomes maybe 100 to 200 gigabytes of data when data is at rest here. So that's one nice thing. You could say there isn't much work done, and it actually happens quite immediately. If we monitor the delay from data enters here to it's actually on disk, typically in our production systems, it's slow when that's 2 seconds, right?
Right. Okay. So it's pretty live.
It's pretty live.
Would you typically recommend SSD storage or spinning disks, or what would you do that? Yeah,
that depends, because then as for ingest, it doesn't matter that much. When we come to queries, then it could make a difference. The nice thing is when we run a query over these, as we'll come back to, because it's compressed here, you only need essentially, as long as you can keep the compressed data that you typically want to query in the file system cache. So a typical running system, that's our deployment model for our SaaS. There are i7 nodes with 64 gigs of memory. And I believe the production cluster is now just a 5-node system. We use on the order of 8 of these to actually run the software, and the rest is actually just allocated to file system cache. Because all this data, when we query it, all the most recent data, either written or read, will then be in the file system cache. Meaning we don't have to spend the time and effort to load it up from disk. That's one of the slow operations, right?
So basically, if the log segment that I'm looking at most of the time can be stored within the file cache, then it doesn't really matter if I use spinning disks or SSD.
Exactly. So if you look at, maybe you use 32 gigabytes of compressed data, that maybe turns into 200 gigabytes of original data. So if your ingest workload is below 200 gigs, then you can have the entire data set in memory. And now, so this is where it becomes interesting, because it's almost an in-memory data processing system, right? So even though, yes, it exists on disks, and these files that are on disk are persisted, etc., the way it operates is almost as if it's an in-memory database, right? Which is also, I know you do part of in-memory database stuff, right? So maybe we should just move on to.
Yeah. So because now we have seen kind of how data gets into the system.
Yes.
Exactly. Let's get our feet wet. Right? Let's try and
let's see what happens when you query stuff, right? Let's see. I'll just remove a little bit of this, because it's almost there's a lot of the same things going on. A little bit here, yeah. So when a query enters the system, there's some user sitting here saying, I want to find all the syslog entries. Maybe he says stuff like, type is syslog. So that's a tag. And I want to find everything that has SSHD in it. And I want, so a query is a sequence like this. And I want to group by the host that sends this query, right? So that's a typical query. How many SSHD log entries do we have by host? Or maybe you want to also find the invalid user. So this is just a free text search, right? In all our syslogs, look for invalid user and say which hosts. So assuming there's you have maybe a couple hundred hosts, which of them, maybe some of them are being attacked, or somebody tries to do an SSH.
This is where I would, typically in the old days do grep pipe,
yes.
cut.
But here, since we have all the data together, we could do that in this way. So when a query comes in, the API logic here, it essentially has in memory a data structure, which is this index of all the segments, right? So it has a segment ID, some tags, and a start time and an end time. So it has just a long list of these, right? So that's the index that we hold in memory, right? That gets loaded up on start and then also appended to and managed, but it's relatively quick to run through this. So as we look, there's a tag here, so we can actually go through this and filter out all the ones where syslog appears in these tags, right? Or type equals syslog, right? So that maybe that filters out some segments, so we don't have to search all of it. And then also when you send a query in, I say maybe last 24 hours. So you also specify a time interval. And maybe also the time interval, based on these start and end times, reduces the set of segments that you're interested in searching. So essentially the first thing that happens after we parse the query and validate that it's syntactically correct is to compute the set of segment IDs that we need to scan. And as I said in the beginning, what actually happens then we pass this to the data subsystem, this list of segment IDs. And this query, the real query is here, where we say I want to filter on something that says SSHD and invalid user, and then I want to group by the host. In this case, maybe the host that sent this log entry. So the first thing we do to speed things up, you could say, is to reduce the set of segments. Right? We reduce the working set, right, by time interval and these tags. That typically reduces the working set to a lot fewer than everything. Right? So you don't need to do a table scan of the entire world, maybe just 1 or 2%.
Okay, so basically, yeah. So and basically, if you say instead of this time window, if you say that till current time, then I will kind of have these live queries, right? These state machines you mentioned before.
Yes.
Yeah.
But let's look at kind of historical queries, how they work, because then the rest here is just, you can imagine a function that just says, does SSHD appear in this log line? Does invalid user appear in this log line? And if it does, we add it to a hash table where the host attribute is the key, the host that sent the log entry maybe. And what we compute is then, maybe we have just a counter in this particular context. They would just count how many times that happens. There's you can specify an aggregate function that gets computed over that. So that's the core of the state machine, right? That really just gets fed all the log lines that match these criteria.
So basically the end result will be like a list of hosts and then how many times did invalid user appear in SSHD.
Exactly. So, so that's the first trick to make it run fast, right? Is to really just only search
boil it down.
Part of the data set, right? The next is then, if we go back to where we were before, and now we're in processing, essentially MapReduce style, processing one of these segment files, right? What happens in here is we take one of these blocks one at a time. So that's, again, remember, it's compressed on-disk storage, but typically loaded into
the file cache.
Into the file system cache. So we decompress it into the original block or sequence of log lines, and then really just do text processing.
So, but I would think that decompressing it takes some time. So there's some kind of a trade-off here, right? Because if it was not compressed, then I wouldn't have to decompress it.
Yes, and the trade-off is that when it compresses nicely, you can keep a lot more in the working memory, right? If all this needed to be loaded from disk. So if you take the case, and actually I have a blog post about this, where if you take the case of just scanning through one, scan through 1 gigabyte of data, right? 1 gigabyte of data, a typical SSD, that takes 1 second to load, actually. So the typical SSD speed is 1 gig per second. Right? Yeah. So let's say this is 1 second, and then a scan of this is, I don't remember the numbers exactly. We'll have to go back to the blog post and see. Look, but maybe 0.1 second to do, say, the equivalent of a grep or a search in that, right? But if you compress it, if it's compressed on SSD, then assuming somebody compressed it beforehand, of course, now we're moving, some workload. That's the workload we actually move to ingest time.
Right.
Compress it so it fills 1/10 of that on disk, then it takes 0.1 second to load it in from disk. And maybe decompression here takes 0.5. Again, you can find the specific numbers in my blog post, and then actually scanning it is 0.1. So we're still, just by loading the compressed and then decompressing it, it's a lot faster than actually.
Yeah, so it's actually both faster, and then the disk footprint is a lot lower, right?
Yes, and it happens so that you get a much bigger working set that you can fit in memory.
Right.
Yeah. Right, in the file system cache. So there's a trade-off here where actually we see the better data compresses, the faster we can run.
That's pretty interesting. I'm looking forward to read that blog post.
So, and of course, as you can see, these segment IDs gets sent to the data engine, and now it becomes kind of a simple MapReduce problem, right? Because this is parallelizable. Finding everything that matches this and this, and doing a counting of how many times logs happen from host. That's actually a problem that you can easily distribute, right? In this case, you want to distribute it among, say, the 4 cores of your i7, right? So if you have a 4-core system, we set up 4 pipelines that run these concurrently. So you can run it 4 times faster. And yeah, there's a lot of intricacies in this where you can optimize a lot more. One of the things that you can do is this data set. So each of these cores, right, they have, it's one CPU, but each of them have its own level 2 cache. Right. Each core has its own level 2 cache, and they share a level 3 cache. So the memory subsystems becomes interesting at this point, right? Where if you have something on the order of these blocks in our current system are in order of a megabyte, that actually it fits in the level 3 cache.
Ah, okay. So
but if you make the blocks smaller, maybe you could even get them onto the level 2 cache, where memory access is 10 times faster.
So basically, instead of scanning, each core gets one of those large blocks, you kind of take 1 megabyte up and then split it onto those cores. Is that how you did it?
No, actually, at the fine-grained level, we split it in to. It's nice that the same core gets the same sequence of these blocks, right? So we actually split it into segments. So one core gets a segment and runs with that.
Okay. Yeah.
And if you have a lot of data, then it easily parallelizes because there's so many segments. Each of these is only 1 gig of compressed data. So that's maybe. So what we see is the ratio that we scan is on the order of 6 gigabytes per second on a 4-core node like this. So that's like 6 times the disk speed, which is still pretty good, right?
Yeah, that's pretty awesome. So, but yeah, and in the end, this could maybe even be further parallelized by going, on multiple hosts or.
Yes, and of course that's the big new thing we've been working on the last 6 months on building out this scale out solution. So typical setup we've had up till this summer were these single node systems where the limit really is about 1 terabyte of data.
Yeah. And that's kind of what we are running today.
Yes. Yeah. So if you need more than that, or if you need more query speed, because 6 gigabyte a second, if you have a lot of data, it might still not be fast enough. Then you can run our cluster solution, which is all of these issues, or these problems here, are actually relatively straightforwardly parallelizable and distributable. Of course, the devil is always in the detail, right? But so a cluster solution would have multiple one of these, right? So each box, let me draw the red boxes again. Each of these would be in a typical setup, a host running this, and a host running this. Again, an API node and a data node. And the index that I showed you here actually also contains which host has a given segment. Right, so
Okay, so basically this header here.
This header here and the little index that we load into memory on all these API nodes, it knows for a given segment who has a copy of that. There can be multiple copies. So when a query comes in, again, you compute the segment ID, say, comma host set, right? And then just send a query to this host, a query here, and then aggregate the results. And that's, so you can say, how do you aggregate a query? And that's
right, yeah, so one thing is to have them all calculated, but you also need to kind of bring it all together.
You need to bring them all together, right? And that involves having all these aggregate states that we compute are mergeable. So that's a classical MapReduce discipline of having mergeable data structures, right? So for instance, if you compute the average of something, right, then here we would compute the count and the sum. And the count and the sum. and a count and sum. And so that's the internal state of the average function.
Right,
and then you can bring all these three to the coordinating node here, compute the total count and the total sum, and then the average number that you need to bring. So actually all our data structures, everything that we can compute, are expressed as these mergeable data structures. And that means, that means sometimes you need to cheat a little bit or go probabilistic, right? So, for instance, if you do count unique,
yeah, that can be problematic.
Then, if to do that precisely or exactly or correctly, you would actually need to move all the unique values to one place to determine precisely. Yeah. But here we use a hyperlog, which is a data structure that can probabilistically compute count unique. So when the number gets big, when you have many things to count, then it's more precise than for smaller numbers. So it's difficult to get a count unique value of that are relatively small. But so some of them are probabilistic. That's count unique. There is a count distinct, yeah. And also the same for percentiles. If you want to compute percentiles of response times or something, you can compute. There's similar data structures that can get merged. And actually, so this mergeable state of hyperlogs or averages like this, that also is how we operate at the micro level. So so within a single node, when we distribute a workload across cores, they compute also in the same way, a mergeable state that gets merged into the...
It's the same problem you're solving, just at a higher level, right?
Exactly.
Yeah.
So being built that way at the core, actually was, the hard part about building out the cloud, the distributed solution wasn't really making these queries work, because that was basically built into the system already. The hard part is the operations of a cluster solution.
Right. So what happens on the ingest side? So let's say I have 3 of those. Mm-hmm. Can I just ingest anywhere, or
yes.
Would I put a load balancer, or what would I do?
Well, typically, so we run it with a load balancer in front, which is a web load balancer that we also run on each node, or outside, even further out. So we have a web server for SSL termination, or a load balancer further out, depending on the setup. But really it doesn't matter which node you hit. You can ingest the data everywhere. And then, so getting back to what we had before, these queues, right? The Kafka queue it'll be essentially available everywhere.
So that's like the same Kafka cluster.
The same, actually. And really what we sometimes like to say, the only piece of really distributed infrastructure that we run is Kafka. We try to stay out of building coordination or building synchronization at that level. We actually handle all that through Kafka. Because this global state, to update this, whenever you write a segment, in order to update this, we have one global Kafka queue that you need to set up in your Kafka cluster. The ingest system will write a command here, say, create an entry for this segment with these timestamps, blah, blah, blah. And all of these global data things here, right? So this is like CRD, this is CQRS-like, right? They just sit, this is really just a state machine that eats index updates from that queue.
So, and then this basically also answers my next question, which would be, what happens if I take one of those guys away?
Yes. So that's one of the things we try to. We're still improving, but essentially right now we just permit one node to go away. The Kafka subsystem, as long as the Kafka subsystem survives, either internally to Humio or separate. We'll continue to ingest, because then Kafka itself kind of does failover of its partition handling, etc. As far as queries go, when you issue a query on a system where one node is down, you get a warning in the UI saying, if one node goes down, there is one of the nodes that's not there, so you probably have incomplete results because all the segments that were only present on that node.
Right. Yeah. So basically, the segments are distributed among the nodes and are on local storage.
So on ingest, so there's a little more. Now it's starting to get a little messy here. Maybe we should. Let's clean up all this mess in the middle here. Right. So just quickly. So the real story with Kafka here is. Logically, it's not like there's one queue on every node. Actually, in terms of Kafka, from Kafka's perspective, there is one queue, which is really a number of partitions. So this is all one Kafka queue, or one Kafka topic, that just happens to have maybe 32 partitions, right? And whenever a log line enters here, we'll take the tags, the combination of tags, and sort them and hash them. And basically just use consistent hashing to assign the log line to one of these partitions. Right? So one Kafka topic really consists of a number of different queues. You can configure this yourself. Right? And then on the other side over here, the data node which are ingesting, there's an allocation. So each of these segments only is consumed on exactly one node. There's only one node that pulls data from each of these segments. And actually this mapping, when you start up the system, there's a pre-computed mapping, but you can go configure that. So if it happens that this one gets a bit overloaded, because all of a sudden there's a lot of data that happens to hash to one of these queues, you can actually go in our configuration and say, oh, I want to have this one consume that data instead. So you can move the ingest load a bit. Yeah. Because in the node where you ingest, where you put stuff in these segments, is also where the state machine that make up the streaming queries, they're also executed there. So if there happens to be a lot of these state machines that are running on one machine, then you can distribute the load. You can also create more segments and distribute the load. So in terms of the cloud solution, the cluster solution, right? There is a scale of both query and ingest. There's resilience, which is you can configure actually once it's done ingesting and has built a segment like this. How many copies do you want stored? Right. So it'll say, send a copy here and keep one for itself. So you get 2 copies. So basically you get a replication factor. And the same, of course, you can control your Kafka, how much resilience you want in that, because in addition to these partitioning schemes, you can also have replicas of each partition, and there's a lot of nuts and bolts you can turn on that.
Yeah, and that's probably beyond, so our workload is maybe something like, I don't know, 20 gigs a day or something, but definitely there's possibility to throw a lot more data at it than that.
So we have some customers that have lots of terabytes of data, right? And it often happens in bursts. And this is an issue if your system is breaking down, or there's some issue in your system, there is a cyber attack, or there is a big bug somehow in your system. These systems will tend to generate a lot of logs. So you want that, be able to consume that spike in traffic, right? And then, in terms of this cluster stuff, there is the fault tolerance. So that's always a complex story because it's not the kind of system where it just keeps running because it kind of degrades its behavior. As nodes go down, maybe some of the data is not available. You still want to be able to access that data. You just get a warning, right? So if you still have a copy of it somewhere around, then you're fine. But if there's some parts of it that you can see are missing, then you get these warnings.
Right, and this is when I would want to have my offline, if I have a copy offline, which we actually don't today, which I maybe should, I could then, bring that back and then get the node up again.
Exactly, yeah. So I think we've about spent our time.
This was super interesting.
So it's a big complex system, yeah. So we run the large clustered solution on our own SaaS, of course, and we have customers running it also on premise. So it was really built to be relatively easy to deploy, right? Because we come from a background of needing stuff like this ourselves and seeing these complexities. So.